Okay, all right. So we are the row group with my my coworkers and individuals back there. You can raise your hand. All right. So we've been working with continuously monitored glucose data. So this problem was motivated by the fact that many wearable devices now can collect large amounts of continuously monitored data, such as fitness trackers and heart rate monitors. And there's an interest in understanding how can we go about analyzing this data without aggregating over the time observations. So for example, a continuous glucose monitor, or CGM, is able to monitor an individual's glucose levels every 5 minutes. So in a day period, that would allow for 288 observations per person. Within a 1 week period, that's around 2,000 observations. With about a month period, you're going to get around 8,000 observations. If I click on this link, okay, so this animation is showing you the glucose values being recorded over the course of a day for 10 different individuals. So you can see how if you have studies that go for a large number of individuals and maybe over weeks or months, the amount of data is going to accumulate very quickly. The data set that we've been working with is from a clinical trial that was interested in comparing two different types of ways to monitor glucose levels in individuals with type 1 diabetes. So the first way is the CGM that I've already mentioned. The second way is using both CGM and the more traditional approach called BGM, or blood glucose monitoring. And they were interested in understanding if using CGM on its own is as safe and effective as using both of them together. So this data has actually been analyzed before using more of the traditional methods with these large data sets where they compute summary statistics such as treatment means or area under the curve for the two different groups. You could imagine something like you see in the image on the left here, where you could then compare the means between the groups. We're interested, though, in being able to actually leave the data in its original format, and instead of aggregating over it, being able to create some functions that we can then compare between the two treatment groups, so you can maybe gain some additional insight into the data that you wouldn't be able to gain with aggregating over the time periods. So to describe the clinical trial a little bit more, the first part included a run-in phase in which individuals came in for training and baseline measurements. At the time point referred to as week 0, they were randomized into one of the two groups, either CGM or CGM plus BGM, where they were twice as likely to be put into the CGM only group. Then they were required to come in for 5 different visits after that point over the course of the various weeks. And so there were 226 individuals in the study. With the original data set, that's around 15 million observations. We chose to only work with about 3 days around each of the visits. So this image shows, kind of gives you an idea of what the data we're working with. This is for one individual. Each of these lines represents the glucose values measured over the course of a day. It's divided into the 6 different visit periods that we're working with, and there are 3 lines within each of those visit periods representing 3 different days that we're going to be using for replication. And as you can see, there's a lot of variability, actually, even just within one individual. So we're hoping the models can also be able to separate the noise, the signal from the noise in the data. Okay.
So our group has developed several methods. I will introduce you with the first part, that intensive longitudinal data analysis. So actually, the longitudinal model, they don't require for that you have to be the whole data set. It's allowing for the missing value. And I need to please keep in mind that our data structure actually is a 3-level data structure. You will see that our days are nesting in visits, are nesting in subject. Our first model is the marginal model with GE approach. Actually, this model is solving the equation 2 in order to get the estimate. So you will find actually this is a non-parametric method, and it's very robust, but it can only deal with 2 levels data structure. And the second model is the mixed model with different levels variation. So we can use it to completely suit our 3 data structure model. And you see here we have the equation 4 for the likelihood. So we have to make larger computation because we have two intervals in the likelihood. And also, this model may be more suitable and accurate when you have multiple levels data structure. So, but this is the way that we fix parameter, and we want to modeling our group different, that is time varying. So time varying means we need to change our time coefficient into by utilize the base expansion. And in our approach, we always prefer the B-spline, so which is the piecewise polynomial function. And in my longitudinal modeling, I choose the cubic spline with degree 3 and the nuts to be 7. So if you have any question, we can explain later. So next thing is we want to see some result from the first model, that is a marginal model with GE. As I say that GE can only deal with 2 level state structures, so I fix the date here. So there is 2 lines means 2 groups. So you will see that the 2 groups actually may detect a little bit different at very, very early morning, but not at daytime. And also the data I used for the application is 60 people, and they are 3 days observed, 3 visits. Also, we use the same data set into the mixed model that with the introduced 2 random effects from the subject level and the visitor level. So we will see it actually also could detect a very small group difference and at the beginning of a day, but not very much in the daytime. So I will say this result actually need to be further tested by the whole data set. We have a very large whole data set, but we do not use it. And also it needs to be tested to see if it still hold by adjust by other covariates also. And I will say what you may ask, what's the difference between these 2 models? I will say they have their own advantages and disadvantages. But which one is better, I think just depend on the data structure and also the research question. But they seem to detect some similar results in our data application. And my teammates, they also have treated the data as another method is functional data analysis. So they will give you some new ideas.
So, like B said, we were also interested in investigating a different kind of approach to try and see if we can uncover different kinds of patterns from these data, and that's from this framework of functional data analysis. So I'll tee up the kind of idea of FDA, and I'm not going to talk about the actual modeling results. Juna is going to do that, but I'll discuss a couple of pre-processing steps that we needed to step through before Juna could run her FDA models. So this kind of gives you a quick flowchart of the data pre-processing steps that we used before we fit these FDA models. And it requires maybe a bit of a perspective shift when we start thinking about functional data analysis. Instead of thinking about patient data as these kinds of collections of pointwise observations that have some dependency structure associated with them, we're now thinking about patient data as these kind of functional curves that have simply been discretized over some fixed time frame, right? So it's a bit of a perspective shift in terms of thinking about the kind of data that we're working with and what form it takes. So a couple of steps. We had to do some missing data imputation and then some functional alignment of these patient curves prior to fitting the FDA model. I'll talk through those in turn. So first up is this missing data imputation problem. So in our trimmed data set, we used approximately, in our trimmed data set, approximately 1.5% of glucose measurements were actually missing across all of our patients. An issue is that no missing values are actually allowed in our selected functional alignment framework, along with one of the FDA modeling approaches that we tried. So the solution was kind of a simple one. We're going to use linear interpolation to impute these missing observations in our patient glucose level curves so we can fill in some of these time gaps. So a quick example to give you some flavor of what that linear interpolation actually looks like. At top, we have an example patient curve prior to linear imputation. We can see that these devices are oftentimes dropping glucose measurements for short or potentially longer time intervals, depending on the kind of user who's actually using these different kinds of recording measurements. And then afterwards, we can see that we filled in these gaps using this linear imputation. And for these small gaps, it seems like it's not totally unreasonable to go with something this simple. So after doing the missing data imputation, we move on to this functional alignment step, and it's really an important one in functional data analysis. The idea here is that we're interested in moving phase variation, we call it, from a collection of observed functions that we assume are generated from the same underlying system process. So another way of thinking about this is that we're interested in aligning these kind of noisy clock time functional observations to some global system time that we think truly dictates the underlying process that generates these patient curves. So there are a number of functional alignment frameworks out there by which you can do this functional alignment step. We ended up choosing a square root velocity function framework to align our patient curves. It's well studied in the shape analysis literature, and it confers nice properties in ways that some other frameworks do not. So we can take a look at what this SRBF alignment is actually doing with some example patient data. So here we've got a collection of 10 patient curves prior to alignment over a 24-hour period, and it looks like we have kind of a colorful plate of spaghetti here, right? So these patients have different lifestyle habits. They're eating meals at different times, which causes peaks at varying times. And then maybe they're expending energy also at different times based on differing activity levels and just having different schedules throughout their days, which corresponds to some of the troughs, right? So imagine if you want to take some kind of summary statistic from these functional data. You would hope that summary statistic, maybe a mean, is reflective of the kinds of trends that you see in each of these individual curves. But if you take a simple cross-sectional mean of this kind of pile of functions right now, you might get something that doesn't adequately capture any of the kind of peaks and valleys that we're seeing happening across all these patient curves just at different time points. So at bottom, once we do this functional alignment, you can see that we're kind of uncovering some of these peaks and troughs in a much nicer way. If we take a cross-sectional mean of now this bottom function, or this bottom collection of functions after alignment, that resulting mean function is maybe going to be a useful kind of summary statistic for us, because that mean function is going to also capture some of these global features we're seeing among these different individuals that were simply masked by this time dimension effect. So SRBF alignment is actually a highly nonlinear process. We're stretching and compressing these functions over different intervals along the length of each of these curves. And so this picture is just a plot of the warp paths associated with each of the functions going from before alignment to after alignment. The wiggliness that you see in each of these curves about that 45-degree line suggests that there's, again, this high degree of nonlinearity in the warping path going from before alignment to after alignment.
So now we move on to functional data analysis after alignment. So we would like to estimate the curve of glucose levels during 24-hour of a period of day for each individual from each group at a given visit date. For estimation, first of all, we do not assume any underlying error distributions. Instead, we use the cubic B-spline where the nuts were placed in every 30 minutes during 24 hours. It is because we would like to fit the data as closely as possible. Since we consider 50 basis functions to estimate the individual curves from each group, fitted model becomes more complex. So we would like to impose some smoothness for our model complexity so that the data is fitted smoothly. Here's the idea for the roughness penalty. So Based on generalized cross-validation procedure, we choose the smoothing parameter lambda as a 100. So we can get the large number of basis functions as well as the smoothness on our model complexity. So this is the graph for one individual person, estimated curve from CGM BGM group and after alignment at the visit 4. X-axis is the system time, not the noisy clock time, and the y-axis is the glucose level in a daily. The point is observation, and then the line is estimated curve. So you can see our estimated curve is very quite fitting well to the observation. So the deviation between observation and estimated curve is very quite small. So our model pretty very well. So next slide is the graphs of estimated group mean curves with plus minus 1 standard deviation errors, and the red line is for CGM only, and the blue line is for the CGM plus BGM group. So as you noticed here, we found after alignment, we found very little vertical deviation between the two estimated group mean curves. So this tells us that there is not much evidence of difference between two groups in terms of system time. So we actually wanted to test this claim using functional t-test. Since we do not assume any error distribution, so we use the non-parametric approach, which is the permutation approach. We test functional t-test through the permutation approach. The red line is observed test statistic, and the blue dashed line is the point-to-point of 5 critical values from the permutation approach, and then the black line is the maximum point of 5 critical values. As you notice, the observed test statistics did not exceed either point-wise point of 5 critical value or maximum point of 5 critical value. So this tells us there is no significant deviation between two mean group curves across the system time, and which aligns with the previous graph, because we also noticed that there is not much deviation between the two group estimated mean curves. And then Catherine will talk about the summary and future work.
Okay. All right. So to summarize what we did, we applied the approaches of GE, IMSS, and FDA to be able to compare functional trends between the two groups. We ran into some limitations, and this leads to future work. Is that we were only able to use portions of the data due to the fact that a lot of these methods were very computationally intensive. It was also difficult to capture some of the full correlation structure with these models. There possibly could be better ways to impute and handle the missing data issue. And lastly, we didn't get around to including any covariance in the model, which might be something of interest. Okay, and lastly, this is a picture of us at the Hunt Library. So, any questions?
Questions for the world group? Oh, sorry. I was looking over here first. Yeah.
On slide 21, your Federal Drug Administration fund, this is about work. I have a question. Do you use the Warpath Analysis to actually start to categorize or classify either body types or lifestyle? Like the amount of warp needed or the amount of alignment needed to put someone with the other group, can that tell you about people?
That's an interesting thought. We hadn't really considered that, but yeah, that's a cool way of thinking about using this information in maybe a more meaningful way. Yeah, I guess honestly, in the shape analysis literature, what we did is slightly different from if you wanted to fully integrate this RPF alignment into doing like a full-on statistical analysis, right? So we selected like a baseline patient curve based on this kind of idea of, we think that you might eat 3 meals a day generally, maybe you have a snack in there also. So we might expect to see 3 or 4 big peaks throughout a 24-hour period for like an ideal patient, right? So we chose a baseline patient curve that we believe reflected that kind of idea qualitatively from our data set, and then we aligned the rest of the patient curves to that function. We did that because doing it the kind of maybe more vertically integrated way, when you're using this SRBF alignment in full, it's super computationally intensive. It requires working with the quotient space after you've accounted for these warping functions, computing some kind of centroid, and then using a dynamic programming algorithm to align all these functions to some global mean, right? So I think if we go down that route, then we could really start to think about using exactly the idea that you suggested to extract some more meaning out of these warpaths and use them in interstitials. So maybe through some kind of distance computation or calculation on this quotient space with these warpaths would be really interesting to look at. Yeah, great idea.
I actually have, like, probably in similar lines, I was trying to think of how you could use this for prediction, because what you essentially seem to be doing is all the uncertainty from the glucose data is sort of transferred to the way you warp the...
Totally, yeah, totally, exactly. And so again, like, limitation of our approach, again, due to this computational ceiling that we had to deal with. In other words, we were running these on our laptops and not with nice compute resources. I think the points that the both of you were making is that we can probably make much better use of these working paths themselves.
Actually, yeah. So what my question actually was, were you able to track for the same patient across different visits or across different days if their warpings are similar, like they stay the same?
We didn't look at that so much. Kind of based on the way in which we approached modeling the correlation structure. Ultimately, we ended up really looking within individual visit days, and so we didn't use the information in a way that would have been probably really nice to.
So we incorporate the correlation structure in the longitudinal models. Actually, we still may have some other correlation that need to be further examined, but in those things, I think is another way of the more focus on the gluten value itself, and not the treatment.
I've got another really good question on it. You put up the slide where you did the alignment before and after. You had that one, yeah. So, the bottom one looks really nice, but I guess this warping means that you're skewing things in this direction, the horizontal direction
in
as
the
well,
time
right?
direction, yeah.
So in a way, you're kind of losing the meaning of some time varying things, like the rates at which a curve drops, right? You're losing that information. So,
At least in the way that the data were originally recorded, right?
So what I'm wondering is that is it not possible to create a surrogate for the data set where you just record the heights of the peaks, the troughs, and the time intervals between them? And you would have a lot less data. You would still capture the features that you're losing anyways by doing the warping. I know it's not for this project, but I think that effectively you're losing a bunch of information that suggests that you could create a feature version of each.
I think I understand what you're saying, but I think the advantage of using this SRBF alignment is that we're still respecting the time dimension in some way. When we're thinking about casting it in like the FDA framework, the kind of summary objects that we might want to use, we would, I think, ideally like to be able to use functions that still respect some kind of time.
Okay, and because you keep the warping information.
Yeah, right, exactly.
That's the mapping.
Right.
That's fair.
All right, any other questions?
Go ahead.
You talked about how you kind of had some dropouts in the data, and then you literally linearly interpolated over there.
Yeah.
Did you have any kind of rule for a maximum time period that you thought it would be realistic to interpolate over?
So we did some high-level filtering for patients who were missing like much of a visit period. We eliminated those people from the get-go because you would have had a horizontal line. You may not have even had like a starting position for some of these physicians to do, for some of these patients to do that. So beyond that, I mean, we kind of did, again, like maybe a qualitative check to see how silly is this imputation. And in some cases, it was quite silly, right? A patient might end up dropping all these observations when they went to bed. I don't know, they rolled over on their device or something and stopped recording. So in those cases, if it was at the end of that 3-day consecutive period, that imputing just was a line. And so there's the question, I think, if we go back to using this SRVF framework as it's originally intended, if we can start getting some kind of, say, mean function within a patient, say cross visits or something like that, that might give us some sense of their individual behavior, we could probably do this imputation in a much better way. And so that's something that we thought about for sure, but didn't get around to it.
Okay, comment from Houston and Petra.
It's been a really exciting results from the students' work throughout the week. We are confronted with this type of data more often as we gather more and more devices. And I feel that this is an area that their ideas will allow us to bring back some of their ideas, their code, to do some of the analysis of our own data. So we are very pleased, and we want to congratulate them for their efforts.
Great. Awesome. Okay, so let's thank